Let us see what we have today. We are going to discuss regarding the sequential circuits and first part SR latch and D latch. We will introduce today. Um, this chapter need more task, more concentration, and more study. The best reference for that is your book. Also for last chapter also. Your book is very good for this. Please read it carefully, and if you have question, then ask me. Anyway, first of all, we should again remind what is sequential logic circuits, which these type of circuits is, as you can see, the output state of sequential logic circuits is a function of three parts. What is that present input? What is that past input? And or the past output, something like that. Then the sequential logic circuits, remember these condition and stay fixed in the current state until the next clock signal change one of the states which giving the sequential logic circuits memory. It means that the performance of our system is the performance of system is based on the pulse. As last lecture I show you what is pulse. I prepare even one video for you to see that how we should work with pulse. It will share maybe tomorrow, and you should see that how the pulse will act and how we should calculate. But today also we are discuss regarding that shapes also again. Anyway, some simple sequential logic circuits can be concentrate, constructed from the standard vestibular circuits such as flip-flop, latch, and counter. Means that in our sequential logic circuits, we have mm, the important one is flip-flops, latch, and counters, and which themselves can be made by simply connecting together some universal NAND gate and or NOR gates in the particular combinational way to produce the required sequential circuit. Again, here I show we have one source of clock, as you can see here, which is entered to the memory. And from this memory, we have something like feedback from our inputs and out. It shows again here the block diagram of our sequential circuits and the timing diagram, which we know as the clock here. This timing diagram and timing circuit, it's something like um, not a reference, or exactly it's something like a reference for us. And as we discussed, we have some specific part or a specific sequence that we will see the performance of our circuits. There are two type of memory elements based on the triggering and in the sequential logic circuits. One is latch and another one is flip-flops. And you know that latch operates with the enable signal, which is level sensitive, whereas flip-flops are edge sensitive. Last lecture, I tell you the level is that we will see the high and low, and for the edge, we are going to rising or increasing or decreasing. Okay, and remember that the difference between the latch and flip-flops is exactly that in which part of clock pulse we will look to the uh, Circuit's performance. Suppose if I look to that just from the changing the level, it's latch. And if I look to that from the edge, it's flip-flop. This is the first difference between latch and flip-flops that I want that you remember that. But thing is that where we to store the info. Let us start from this point or something like feedback. What is that? If we put two inverter or two NOT gate sequentially together, they can hold a bit as long as power is applied. You will see that they can store the value. Suppose if I put the one at the entry of these gates, it's first it's become zero, second it's become one. Okay, and it's exactly like the feedback that you will see here. Storing the new memory or temporarily break the feedback paths. If we will do that, we can have in the second figure, I mean, we can have the form of here. We can have the second or exactly the form of the memory, which is a little bit uh, near to the real one. Means we have one entry here and one feedback here, and we should control them when the data come and when we need to take the remembering part. SR latch will use the NOR gate to construct a stable state network. And as you will see here, we can have the different performance from this. Regularly, we will shows this type of SR latch with this shape as I show here. Or if we want to show it with the block diagram, we will show with the B. But generally, the way that we will show is number 8, and we show it like that. Okay, remember this. Here, I'm going to show you that how it will work. This type of the sequential circuits, as you will see, we can consider four situation. Why four? Because we have two input. One is R and another one is S. Okay. Then first assume the condition which S and R both of them are one. Then the S and R latch will not operate probably. It's a stable state if S and R is one. And then Q and P are complementary. Some people will show this as P, some people will show as 1. Let us suppose check if S is 1, okay, and R is also 1, as you will see here, okay, then we should assume the some previous situation for these two conditions, which mainly they will come from the feedback of uh, output gate of first part and second part for the first. Then if S is equal to R and equal to 1, it will change to S and R to 0. Then the network will oscillate, and assuming will both gates have the same delay, call it a critical race. Okay. Better things to show the performance of this um, SR latch is the waveform that we can see here. Here, as you will see, I have the state of 0 for the S and a state of 0 for the R. Okay. And then Q is also 0. Q is 0, here is 0, and here is 0. If Q is 0, I can bring this 0 here. 0 and 0 NOR, it's become 1, and 1, 1, and 0 and 0 NOR. It means not or. It's become 1. And then this 1 can go up. Then 0 and 1 NOR, it's become 0. Then it's correct. Okay. The output is like this. Then we will see that for the next situation, what will happen. For the next situation, we have 1 and 0. But really, the Q as the output, we cannot have that because there is some delay time that between the performance of next step and generally there is some epsilon time which Q will happen. Then we need some delay between the Q performance and with others. um, Maybe you say that okay, then how we should know this situation of output like that? Generally, there is the table for that that you can memorize it or and you should even practice that to learn. Uh, I will try to put some video regarding this, but you should also read it. Maybe in that video, it's become more clear for you that how the truth table of SR or flip flops will happen. Suppose it's like that. If I assume S is 0 and 1 is 0, but now the construction is based on NAND. It's not based on NOR. Okay, 0 and 1. And I assume that Q is 1, then 1 will come here. Okay. Now first I should calculate the Q prime to use it here. Then 1 and 1 NAND is if that was and that was 1, now NAND is 0, then its Q prime is 0, and this 0 will go there. Okay, then I can put the state here that we call it if S is 0 and R is 1, the output is 1 and 0. We call this state as set. Okay, next situation. If S is equal to 1 and R is equal to 0, and we have the situation for Q as 1. This 1 again here, 1 and 1 and is 1, NAND is 0, then 0 will go there. 1 and 0 is equal to 1. Then my situation is again as 1 and 0. Then if both situation are same, you will see that from set, nothing happened to my output. That is why we call this situation as hold. Then, in the case that we had 1 and 1 in our inputs, the output is hold. Next, I assume S is equal to 1, R is equal to 0, and Q prime is 1. If Q prime is 1, then 1 will come here. S and S prime NAND is 0. 0 will come here. Then my output is 0, 1. 0 and 1. Then for 1 and 0, it should be 0 and 1 here. Yes, let us see. Yes, it's 0 and 1, which we call it reset. Why we call it reset? Because if we compare to the set one, it's exactly complement or not of the output of set mode. Okay, then we call it reset. Next situation is that if S prime is 1, R prime is 1, and Q prime is 1, Q prime is 1, then the NAND between them is become 0. 0 will come here. Then my output is 0 and 1. 0 and 1. You will see that. Again, whatever I have in reset condition, it's again happening. That is why we call it hold. Hold means that the previous situation again repeat. Then remember, whenever S and R in S R latch is on, the previous situation will be repeat or hold or will not change. Okay, remember it. Just now we have one condition, which is S is equal to 0, R is equal to 0, and Q is suppose 1. If Q is 1, then my Q prime is 1. 1 will go here. And again, it's my output is 1 and 1. You will see, yes. This condition is disallowed. Why? Because we cannot have the value of Q and Q prime as the same. We know that Q prime is not for Q. Okay. Then the first thing that we find that we are not accept this. We never can have this situation of 0 and 0. Now, what you should do, you should remember this table. This is the first table that I want that you have. Generally, what I advise for the students, that write the flip-flops tables and latch uh, on a board, and then have all the uh, relation and truth table together, and then memorize it. This is something that last semester also we have done, and it shows the good performance. Please, you also try to note them on. In that video that uh, if I didn't put for the last lectures, again I will record. I will do that, then you can also uh, follow that. Uh, Again, let us see with the NOR gate what will happen. If you see the dots as 1 and block dots as 0, you will see that how my output can be changed. Suppose in the case that S is equal to 1 and R is equal to 0, I tell you that we call this situation as set. In the case that S is 0, R is equal to 0, we call this case hold. Case that S is 0 and R is 1, we call it as reset. S is 1 and R is 1, we call this situation as not allowed. This is nothing but previous uh, table that I give you. Please remember that. Here, this is just some figure which show you the output, and you can see 0, 0, 0, 1, and what will be the output of our SR latch. Okay. Um, what we say that for the SR latch we have two situations. One is that present, and one is that next. Which next is there is some t plus epsilon time, which is as we defined this type of circuits, which the circuits which are depends on the time. Then we should have the t plus some time, as I show you in the figure. The present state, which we call the state of Q output at the time that input signal are applied. And the next state, or the state of Q output after the latch has uh, reached. Here is nothing by previous again uh, table that we have, but here we have some condition like this. If you can see that we can have the present of 0 or 1 and then see the performance of the SR latch. Um, Here again, I show the NOR gate of SR latch, which it shows the performance of this type of uh, sequential circuits, and it's same. But why again I bring it here? Because uh, maybe we will learn also how to present the state like this previous. Just see this, we will discuss about this situation. And here you will see that this is 0 and 0. And we can select between the current inputs of S and R. We call it T because we know that they are depends on the time. And then we can see the states, the various states and various performance of the latch that we have. Based on the true table that we had for the Q prime or Q plus, if you put it in the K map, you can have this relation that we call it the transition equation or characteristics equation of SR latch, which is important. Then the second thing that you should remember is this. The Q prime of the SR latch is S plus R bar Q, which it comes from this K map. Okay. And we call that Q plus is the next state, Q plus, and Q is present state. And S and R, we know that it cannot be one at the same time. We analyze one. And next state equation is something that we show at the top. Um, what will happen really with the NOR gates is that we should use some um, circuits to do the debouncing. What is debouncing is that maybe you see this part of the sound or noise from your house alarm. When you press any push button in the entry or your home, and you just keep your finger on that, you will see that the sound is suddenly come up and down, up and down, up and down like that. To avoid this situation, which we call it bouncing part, we can have some circuits which we, with the help of some resistor, as you will see here, and then based on this situation, which I show here, this is the debouncing up and down. We can remove the noise from our circuit's performance. Remember this, then we will again also discuss further. Okay. Here what I show with the NOR gates, same truth table, same things that I tell you here, but based on the waveform, okay, which is more important for us. And what we say that we have situation of disallowed, we have situation of hold, we have situation of set, and situation of reset. Set and reset are shown better here and hold situation, which it means they remain the previous situation or remain the previous state of our circuits are showing here as you can see. Uh, then, as I say, you should remember these shapes. And again, the something that I show it here, it's based on the parts of 1 and 0. Why I have some different figure? Because I bring it from different source for you to make this subject more simple. Otherwise, the shape are same and truth table is same. Don't be confused. Okay. What you should learn is that suppose this is from your book, is that this is the performance of NOR gate latch and it shows in the truth table. Okay. Now let us speak more for NOR latch circuits, which both inputs should normally be at the logic of 0 level, and changing an input to logic 1 level will force that output to the logic 0. This same logic 0 will also be applied to the second inputs of other NOR gates and allowing that output to rise to logic 1 level. This is turn feedbacks to second inputs of original gates and forcing its output to remain at logic 0 even after some external input is removed. And applying another logic 1 inputs to the same gates will have no further effects on these circuits. However, applying the logic 1 to other gates will cause the same reaction in other direction, thus changing the state of the latch circuit the other way. Note that it's forbidden to have both inputs at logic 1 level at the same time. That state will force both output to logic 0 and overriding the feedback latching action. In this condition, whichever input goes to logic 0 first will lose the control, while the other inputs still at logic 1 control the resulting state of the latch. If both inputs go to 0 simultaneously, the result is the race condition, and the final state of the latch cannot be determined. Then let us see once more what we talked about the S and R latch when S is 0 and Q is 1 and R is equal to 1, then resets is Q is equal to 1. The NAND latch gate has some standard form we show here, and we will show with the S bar and R bar as figure shown. Uh, Again, I show here that with the sets and reset, or it means that with the 1 and 0 as the initial state, uh, what should be the output? It's same. Then the basic RS NAND latch, for that, both inputs should be normally at logic level of 1, and changing the input's logic 0 level will force that output to logic 1. The same logic 1 will also be applied for the second inputs of the other NAND gates and allowing that outputs to fall to logic 0 level. This is in turn feedback to second inputs of original gate and forcing its output to remain at logic 1. Applying another logic 0 inputs to the same gate will have no further effects on the circuits. However, applying the logic 0 to other gates will cause the same reaction in the other direction, thus changing the state of latch circuits the other way. Please note that it's forbidden to have the both inputs logic 0 level at the same time, and that state will force output to a logic 1, uh, overriding the feedback latching action. In this condition, whichever inputs goes to logic 1 first will force control, while the other inputs control the resulting state of latch. And if both inputs go to logic 1 simultaneously, the result is race and final states cannot be determined. That is was the what we saw in the figure. But how we should remove it? We can have some SR latch with some clock signal, which will give this time for us. If I put some or add some part before this some parts before my circuit, and then again we can now compare better the performance. Means that if first part I don't have any clock, then I can say that there is I can see the performance that without clock uh, there is no change, and when clock will happen, then we are going to see the performance of our uh, um, circuits. Uh, Here we will see that if clock is 1, then if my input is 0 and 0, then there is no change. If input is 1 and S and R we have 0 and 1, then Q is 0, 1, and like that. What I want that you check this table with this logic, then you will understand it better. This is your assignment for the next lecture, that you should check this table with the help of uh, the circuits that I give you. Then you can understand it better. I will put it in our lecture group. Then please test it. No need to send for me. Okay. But if you don't test it, you cannot understand it better. Here again, this is what we have with the control inputs part of SR latch, and we show it here. As you see, the clock RS latch circuit is very similar to the basic latch that we have. The S and R inputs are normally at 0 logic and must be changed to logic 1 to change the state of the latch. However, with the third input, a new factor has been added. These inputs is typically uh, mm, designed C or clock because it's typically controlled by the clock circuit of some sort, which is used as synchronize several of these latch circuits with each other. The output can only change state by clock inputs is a logic 1. When clock is a logic 0, the S and R inputs will have no effect. And the same rule about non-activating both S and R inputs simultaneously hold true. If both logics 1, when the clock is also logic 1, the latching action is bypassed and both output will go to logic 1. The difference in this case is that if the clock input drops to logic 0 first and there is no question or doubt, a true race condition will exist and you cannot tell which way the output will come to rest. The example circuits on this page reflects this uncertainty. For correct operation, The selected R or S input should be brought to logic 1, then clock input should be made logic 1 and then logic 0 again. Finally, the selected input should return to 0. This is what we say up to SR logic. Okay, and then I'm going to talk regarding the SD type of the latch. But after this type of SR, we have another type of latch that we call it D. D latch is depends on clock, and then you know that we can have the clock of high or clock of low, and input in the clock high, input passes to the output, and first let me check. Uh, and for the clock low, the latch hold its output. Means it's like this. Whenever you have the clock, it will pass whatever is input. And whenever clock is low, it will latch or hold its output. Latch are level sensitive and transparent. As you will see here, we have the timing diagram that in this timing diagram, you can see that when I have the clock and my input is 1, then the output is 1. Again, for the next one, when clock is down or clock is low, it will latch, means that it will remain, okay, or it will hold. And again, when it's high, it's again transparent, this output, inputs. Here, what will happen? It's come down, our inputs in 1 and 0, but it's again continue the previous uh, clock and so on. It's a nice example. This is exactly something that I going to record one new video based on working with this wave diagram. But here, suppose if you will see, I have 1 and 0 in my inputs, but my clock is low, then it will again continue the previous state that we have, and so on. You can see. Then D is not difficult. D is very simple type of the latch, which is depend on the clock. When clock is present, then the inputs will continue, and whenever it's become down, it will keep or hold the previous state that we have. Okay. If we want to show this latch, it's showing like this with the inputs, output of Q bar, and clock. This is the box and how we will use this fed in future. But what is inside of this D latch? The D latch is combination of some SR latch with the help of AND gate with these formats. And we can see the performance of that um, with the help of waveform and truth table that we mentioned here. Let us see what is that. You'll see that we have the pins of enable and D. Okay. These my inputs. Whenever we don't have any enable, then we don't have no change, nothing will change. Whenever we have enable and D is 0, Q is 0. Whenever we have enable and D is 1, then Q is 1. It's very simple. Table and function table is very simple that you can see here. Uh, this is one very useful variation of RS latch circuits. It's data latch, or which people call it D latch, and it's generally called as shown in the logic diagram in the figure. The D latch is constructed by using the inverted S inputs as the R input signal, and the single remaining input is designed D to distinguish it's operated from other type of latch. It's make No difference that the R input signal is effectively clock to voice, since the clock signal will either allow the signal to pass both gates or it will not. Then you will see here the shape of the D latch. D latch, when clock inputs is logic 1, the Q output will always reflect the logic level present at the D inputs, and no matter how that change. When the clock inputs fall to logic 0, the last state of the D input is trapped and held in the latch for use by whatever other circuits may need this signal. Because the single D inputs is also inverted to provide the signal to reset the latch. These latch circuits cannot experience the race condition caused by all inputs being at the logic 1 simultaneously. Therefore, the D latch circuits can be safely used in any circuits. Although the D latch does not have to be made the edge trigger for safe operation, there are some applications where edge trigger is desirable, and this can be accomplished by using the D latch circuit as the master of RS flip flops, as shown on the next part that I will show you here. You will see that we can have the S bar, R bar, or SR and D type of the flip flops. Here is exactly the triggering for the flip flops that we discussed last part, depending on the level, depending on the edge, with the positive and negative time. And you know that performance of our flip flops are based on exactly this timing diagram. But something that very fast in two slides I will going to discuss and we will finish today lecture is that we have some latch timing problem, which in sequential circuits, some paths may be exit through the combinational logics from one storage element to another and from storage elements back to the same storage element. The combinational logics between the latch output and the latch inputs may be as simple as in interconnect. For clock suppose D latch, the output Q is just depends on the inputs. Uh, the whether the clock input C has the some value, as we saw here. To solving the latch timing problem, we can consider the latching part as I show here, and as long as C is equal to 1, the value of Y continues to change, and the change are based on the delay present on the loop through the connection from Y back to Y. The behavior is something like unacceptable, and you will see that to solve this timing problem, a solution is that to break to close path from Y to Y within the storage elements. And then we have some concept that people will call it master slave flip flop and H trick that we are going to discuss later about these two terms. Just what I want as the summary of today, is that what is SR latch, which construction it has, what is D flip flops, and what is the construction of that, what is the truth table,